Thank you for coming to this session. I'm Shioulin from Cloudera Fast4 Labs, and I led our report on learning with limited label data, so I'm happy to be able to share it with you today. For those of you who are in the room, Ryan, my colleague, just gave an awesome talk on transfer learning for NLP. And our sessions are actually related because transfer learning is obviously one approach that you would use to solve the problem of learning with limited label data. But there are other approaches, and that will be the focus of this talk. Before I start, I just want to give a brief introduction of who we are and what we do. At Cloudera Fast4 Labs, our goal is to bridge the gap between research and machine learning and industry applications. And one of the ways we do that is through publishing research reports. These reports are meant to highlight an emerging capability within machine learning that we believe will become important for the business community within the next 6 months to 2 years from when they're published. Here are a list of reports that we have done in the past. Our subscription clients have access to all of these content along with prototypes that demonstrate each and every one of these capabilities. The second mechanism that we use to tightly couple research and application is our machine learning application development programs. In these projects, we essentially consume our own research and use it to enable our clients to be more innovative and efficient. With that, today I'm going to spend some time to talk through our report, Learning with Limited Label Data, and I'll also show you this really cool prototype that our GUI wizard built. His name is Grant. So let's get started. Supervised machine learning is powerful because it lets us teach machines using examples. But these machines need many, many examples. If you're trying to build a medical diagnosis tool, this implies that all your medical images need to be labeled as positive or negative before the machine can use it to learn. Those of us who work with data know that real-life data doesn't always come nicely packaged with labels. It's messy and unorganized. We actually might have a lot of data, but it's hard to leverage it to build something useful for the enterprise. For financial institutions, risk assessment is crucial because that determines the amount of capital that needs to be set aside to absorb systemic financial risk. Volumes and volumes of loan documents and collateral documents exist and can be used to build such a model, but not very many of these documents have been properly labeled or annotated. In healthcare, we have a lot of medical images, and that can be used to build a diagnostic model. But once again, these images have also not been properly labeled. For corporate IT, we have a lot of chat logs available that can be used to help understand consumer behavior, consumer preferences, but these chat logs also have not been properly labeled. So what should enterprises do with all this data that they're sitting on? Well, one approach is to manually create labels for everything. This is a brute force approach. It's not very efficient. It's also very expensive and not scalable. There has to be a better way. Can we use some kind of intelligence to help us identify what data to create labels for? Can we actually only label data points that will be helpful for the machines? Can we use a small set of labeled data to build a model and have the model perform almost just as well when you compare to a model that we would have built using a much larger data set? The answer is yes. So with active learning, we can take advantage of the collaboration between machines and humans to help us smartly select a small set of unlabeled data to create labels for. We can then build a machine learning model using this small set of data. This opens up new product possibilities that were previously constrained by limited label data and allow enterprises to actually make use of their existing large pools of unlabeled data. Well, active learning actually is not new. It's been around for a while, but recently active learning has been adapted for deep learning, and we think that's very exciting. Along with that is a maturing ecosystem and availability of tooling. So that are some of the reasons of why we're actually discussing active learning. So how does it work? You start with a small set of labeled data. You use the data to build a machine learning model. This model is then used to make predictions for your entire pool of unlabeled data. In the process of making prediction, the model also identifies points that it has the most difficulties with. A human steps in to create a label. This data point becomes a labeled data point. And we add it back to our original labeled data pool, and this process starts again. So this obviously is an iterative process. And if it's working properly, this is what you should expect to see. Over rounds and rounds of active learning, as we have more access to labeled data, you should see a general uptrend in model performance. Now, this improvement doesn't have to happen over each consecutive round of active learning, but if you look over a little bit of a long time frame, the performance should be obviously uptrending. So then the next question is, if it's an iterative process, how do I know when to stop? Good question. So each label actually has a cost of acquisition associated with it. This is the amount of time and money that's required to obtain a label. Some data is easy to label, some not so straightforward. It's easy to label an image as a cat or a dog, for example, but it's not so straightforward if we're trying to label image for automotive insurance claims for damage severity. It requires domain expertise and it requires much more time. So with that in mind, we can think of the stopping criteria as either a static version or a dynamic version. In the static version, we essentially arbitrarily set a budget limit or some kind of model performance target right at the beginning of the active learning process. And we continue to run active learning until we hit one of those metrics. For example, I can say I'm only going to spend $10,000 on labeling data, or I'm going to just keep going until my model performance hits 85% based on accuracy. So these are arbitrary numbers that we kind of just pull out. You can use that approach, but obviously a better approach is to look at the dynamic approach. In the dynamic approach, we are looking at each round of active learning, and we are looking for improvement within each round of active learning. And you stop when an additional round doesn't give you much improvement in terms of the performance target that you're looking at. So that's the basic setup of active learning. At the heart of active learning is a model that's able to identify points that it has difficulties with. How does it do that? It turns out the model relies on some strategies. The simplest strategy is one that I'll point out here. Really, it's random, meaning that there's really no strategy. In this approach, you randomly pick data points to get labels for. This is similar to us, picking a top card from a shuffle deck, requesting a label for that, reshuffling the deck, picking the top card to request labels for next. Now, this approach guarantees you more data, more labeled data, but not necessarily the best set of labeled data. It is still useful, though, for two scenarios. First, when you don't have a lot of labels to begin with, using random sampling allows you to at least get sufficient labels to jumpstart a model. And then upon that model, you can iterate using active learning. The other good thing with random sampling is that it can be used as a baseline benchmark. Anything else should perform better than random sampling. Earlier, I said that the model actually looks through the data points and identifies the one that has the most difficulties with. So points that are difficult can be thought of the ones that the model is most uncertain about. And one way to quantify uncertainty is to use the notion of margin. And I'll illustrate that using an example. So assume I'm trying to build a simple model to classify product reviews into positive or negative reviews. And assume that my model gives a very nice linear decision boundary. That's the pink line you see. And this model only takes in two features, positive words, number of positive words, and the number of negative words. So anything to the right of the pink line, the pink decision boundary, will be classified as positive reviews. And anything to the left will be classified as negative reviews. Now, data points right around the decision boundary are the ones that the model is most uncertain about. Why is that? Any changes in the decision boundary due to model refinement will cause the same points to be classified differently. So if I change the decision boundary from the solid pink to the dotted pink, I'm going to get those question marks will be classified differently under the two different models. Data points that are very far from the decision boundaries are the ones that the model is very certain about, so it's safe from these changes. So when we use margin sampling as a way to select data points, as a strategy to select data points in active learning, What we do is to look through each of the unlabeled data points, use the model to compute the distance between the data point and the decision boundary, and then we just pick the one that's closest to the boundary to request labels for. Knowing information for those data points will help the model become better. Another way that we can use to quantify uncertainty is through the notion of entropy. So entropy formalizes the intuition that outcomes of uncertain events carry more information compared to outcomes of certain events. Let's illustrate that using a simple example. Here's the entropy plot for a coin toss. The maximum entropy is 1, and that happens when we have a fair coin. When you're tossing a fair coin, with equal likelihood, you will get a head or a tail. So you're very uncertain about the outcome. You don't know what it is, which is why we associate an entropy of 1 for that event. Now, think of a scenario where I'm tossing a double-headed coin. There's no uncertainty in that event. I toss it. I know I'm going to get a head, so there's 0 entropy. The same applies for a double-tailed coin. When I'm tossing a double-tailed coin, I know I'm going to get a tail, so my entropy is 0. How do we translate this into machine learning models? Assume I'm trying to build a model to predict the outcome over 10 classes. And let's say I built the model and I have 2 data points. The first data point, I'm going to calculate the prediction probability across all these classes, and I get a 0.1 for everything. Now, the second data point, I get a 0.9 for one of the classes and very small probabilities for other remaining. So which one has a higher entropy? The one that has equal probability distributed across all classes. Essentially, the model doesn't know, right? I think it could be any of these classes. So when you compute entropy for that probability, prediction probability, you get a very high entropy measurement. So when we use entropy as a way to select data points to get labels for, what you do then is to run the model on all your unlabeled data points and pick out the ones that has highest entropy and create and request labels for that. So those are our basic active learning selection strategies. They're classical strategies that don't work for deep learning for 2 reasons. Well, first, deep learning trains on batches and is very, very data hungry. So a couple of newly labeled data point really doesn't help it much. Second, many of the existing heuristics don't translate very well directly into the deep learning setting because of the high dimensionality nature. And very often you have to rethink and reinterpret the heuristics. So let's take a look at how we can do that for margin sampling. In margin sampling, what we're trying to do is compute the distance between a data point and a decision boundary, and then we pick the ones that's closest to the decision boundary to get labels for. Computing this distance is not tractable for deep learning models because of the high dimensionality nature and the very complex nonlinear boundaries. So what we could do, though, is to compute the distance between the data point and the closest neighbor of a different class. This computation is expensive. It's doable, but it only gives us a very coarse estimate to the actual distance that we're looking for. What we're looking for is the distance between that point and the pink line. What we're getting is the distance between the flower and the fish. A more creative way is to use adversarial perturbations to estimate the distance. Perturbations happen when a small noise added to an input to a neural network will cause it to misclassify. If I add a small noise to an image of a panda and I feed that resulting image into a neural network, it will get misclassified as a gibbon, and it gets misclassified with high confidence. To a human, both images on the left and right are pandas, but to the computer now, it's no longer a panda, it's a gibbon. So the idea then is to essentially look for the smallest perturbation that will cause a data point to switch classes, to misclassify. Once it misclassifies, essentially switch class essentially has hit the decision boundary. So we can then use the magnitude of the perturbation as a way to estimate the distance between the data point and the decision boundary. This, because you have to perform this perturbation for all the unlabeled data points, depending on what kind of perturbations you use, this could also take a while. So is there a different way that we should look at uncertainty in neural networks? Let's go back to the basics. For those of you who remember Bayesian, With Bayesian neural networks, you can actually obtain this posterior distribution. This is essentially the probability distribution of weights for a particular neural network. Now, once you have this posterior, you can then write the uncertainty of the neural network, which is expressed as the prediction probability given the training data and the input, as a very nice mathematical formula. Now, this formula is very pretty to look at. It involves an integral. It's not very easy to compute, and you actually have to implement the Bayesian neural network to get this posterior. So can we do it a different way? Turns out, you can actually use dropout as a way to estimate the posterior. With this dropout approach, the expression for prediction probability simplifies into a very easy to compute formula. So then, instead of using Bayesian network, let's use dropout. So how do we use dropout for this purpose? When we use dropout to estimate the sample the neural network, what we do is essentially leave dropout turned on during inference, and you run multiple passes of inference through the model. Each inference will give you a set of weights and the likelihood that it happens. If you run it multiple times, what you end up is a plot that shows you weights and the probability of that weight happening. So that is exactly the posterior that we're looking for. To use dropout as a way to help us estimate uncertainty in neural networks, we then essentially do that. We run multiple inferences. Each inference will give us a prediction probability. If we run 10 inferences, we take the 10 different prediction probabilities, take the average of that, and feed it into an entropy approach to figure out which data point we should get labels for. Another approach that is similar is to use the ensemble approach. Now, in the ensemble approach, we are training multiple neural networks at the same time. These neural networks share the same architecture. They're initialized differently. They're trained on the same training data. And when we use this approach to estimate uncertainty in neural networks, we're essentially grabbing the prediction probability of each of these individual ensembles, taking the average, and then using this to feed back into our entropy approach. So the ensemble approach obviously is more computationally expensive because you have to simultaneously train multiple models, but it has been shown to work better when you compare it to the dropout approach. And intuitively, this is because the ensemble approach is sampling from individual independent neural networks, but the dropout approach, you're essentially sampling from the same neural network that's been trained with that one single initialization point. So at this point, we have a pretty good idea of active learning. So let's, I'm going to switch gears and show you our prototype. Hold on one second. No one see this. OK. So for each of our reports, we build a prototype to illustrate the capability. A prototype for this report is publicly available. You can find it at activelearner.fastforlabs.com. The idea is to build something that illustrates the process of active learning, and hopefully through the process provide insights as to how and why it works. And we do it using 3 different data sets. On the top left-hand corner, you see there is an Emnes Dataset, a Quickdraw Dataset, and a Caltech Dataset. It might be a little tiny, but I think the Emnes Dataset doesn't need any introduction. It is the Hello World Dataset for machine learning. The images are essentially handwritten digits from 0 to 9. If you are curious, this is what it looks like. Oh, so 7, here's some 2s, here's some 1s. The next data set that we use is the Quickdraw dataset. The Quickdraw dataset has about 345 categories of hand-drawn doodles. We randomly selected 10 categories, and you can see at the bottom. So we've selected dolphin, cat, face, angel, airplane, apple, broccoli, crayon, bicycle, and elephant. And we build a classifier to classify into one of these 10 categories. Here's just an example of what some of the doodles look like. Here's some crayons. Here's some apples. And here, I'm not sure what that is. That's a face. All right. So the next data set that we looked at is the Caltech Dataset. These are real-life images of things. The original data set has 256 categories. We selected 10 categories at random. So we have cake, dolphin, elephant, Golden Gate Bridge, goldfish, rainbow, teapot, teddy bear, washing machine, and waterfall. These are selected at random. And here's what the images look like. Oh, so here's some elephants. And here are some bridges. OK, so I'm going to go back to the Emnes Dataset. And on each of these data sets, we build a model to classify into 10 categories. And then we use the selection strategies on top to figure out what data to get labels for. The strategies that we're showing include random, which is the baseline, Entropy Approach, which works very well for non-deep learning models. And then the two on the right-hand side, the adversarial and the ensemble, are approaches that's targeted for deep learning. The blob here at the bottom are really just numbers and charts and stats to help you keep track of what's going on with active learning. So what is the blob? What are the blobs in the middle? Those are actually 2D visualizations using UMAP of the embeddings that we grab from the models that we build. So I'm going to walk you through one cycle of active learning so that we can get a sense of what's going on. We'll start with the Emnes data, and then we'll start with the random selection strategy. So for those of you who are familiar with Emnes, the dataset has 60,000 labeled data points. And for the purposes of active learning, we assume that only 5,000 are available. And we use that 5,000 data points to build a model. Here's the output of the model. When you use only 5,000 labeled data points that randomly selected, we get an accuracy of 92%. That kind of tells you how simple the data set is. Now, and the UMAP visualization is over here. So with the UMAP visualization, you're able to see almost very clearly 9 blobs. So each blob essentially has one number. So here are the 1s, here are the 8s, 0s, 6, and so forth. And the gray out data points are essentially the ones that the model is requesting labels for. And this is under random strategy. So let's say the model is actually requesting labels for additional 1,000 data points. And assume now that I have provided the labels for that. I now have 5,000 plus 1,000 data points, and I will use it to run the next round of active learning. So here's what happens when I run it. We see some better separation. And this is using the random selection strategy. Now, what if I use a more sophisticated strategy? So I'm going to use an ensemble approach to help me pick the data points to get labels for. The first thing you notice is that the data points that are requested are no longer randomly scattered all over. They're actually at the border of these blobs, which makes sense because knowing more information about these border cases will help the model be able to separate out the clusters better. So let's do another round. Now, this essentially is requesting data points for additional 1,000 unlabeled data points. Now, assume I've gotten those labels. I'm going to group it back to with my original 6,000 data points. I have now 7,000 labeled data points. I use it to run another round. And then you see better separation. And the accuracy has gone up from 92 to about 96%. Now, this is training using 7,000 labeled data point from the Emnes dataset instead of training a model using 60,000 labeled data points. So what we're seeing is that many of the data points are not super necessary when I'm trying to build a model. I've just been told I have 1 more minute, so I'm going to go through. Here is a different data set. This is a more sophisticated and harder data set for the machine. We do the same thing. We have 65,000 labeled data points, but for this purpose, we only pick 5,000, and everything else we assume we don't have labels for. We train a model. The model, if we do it that way, only has an accuracy of 76%. It doesn't look very clear, the separations. The second thing you notice is that the data points that the selection strategy is requesting labels for are actually clumped in the middle. And that kind of makes sense because what it's trying to do is essentially trying to separate out blobs, but because everything is a big blob, so let's start from the middle and then we try to separate out. So I'll do 1 more round. And then with more labels, you start to see better separations. And then one more round with more labels, you start to see better separation. So this is publicly available. Please play with it after this talk. I just want to leave this up here. For those of you who are interested in learning more, we have the prototype which is publicly available. We also have a series of content on our blog. The first 3 relates to active learning. The 4th one talks about meta-learning. And then the 5th one talks about weak supervision using Snorkel. And that one, we actually have an accompanying notebook that you can play with. If you like podcasts, I did a recording with Twimmel, and you can find that here. We are hiring. If you're interested to find out more, come talk to me after this. And I'll be happy to answer questions outside. Thank you so much.